So we try and drive Cauchy's equation by considering an infinitesimal volume of a fluid flow with its different components. The main equation that we consider is where all the forces are balanced by the momentum forces. And we have mentioned this equation several times in our discussion, so no need to go to repeat too much on this, but just to draw your attention that, as I said a little earlier, we are considering, for simplicity, for convenience, only the x component at the moment of this three-dimensional equation, that there will be components in the y, in the z directions also, but for the moment we are considering only the x component of all the variables that are acting. So the total forces on the left hand side, and they are mainly the sum of body forces and the surface forces, and on the right hand side are momentum forces, and beta is the flux correction factor that we discussed in Reynolds transport theorem when we were considering that. So as the control volume shrinks to a small point, the first term on the right hand side of the above equation becomes, so this is the first term, and that will be approximately, this is showing, approximately equal to rho u into dV when written in its component form will be dx dy into dz, and since the volume of the differential element is dx into dy by dz, that is, that this is equal to dx dy dz, the volume, length into breadth into height. So if we are considering a small infinitesimal volume of the fluid with the dimensions dx, dy, dz, that their product will reflect us the volume, and the small infinitesimal volume product will be equated by this. That is why these three numbers. And one can see that this type of product will be appearing in all terms in other directions as well. So this really reflects the rate of change of x momentum within the control volume that we are considering. The net outflow of x momentum, that is, outflow of the momentum in the x direction through the control surface, will be this place. The momentum moving out, the value of the momentum at the outer, at exit, and minus what it was at the inlet point. The difference of the two will give us the rate of change or the change in the outflow. So what we call here as net outflow through the control surface. For the forces side, the gravitational force normally acts in the vertical direction. We know it. But it is not necessary, and as we will show you a little later, it can have components. So in general form, we have to write all its three components in x, y, z directions, in which correspondingly I, j, k are unit vectors. And likewise, the body forces, therefore, Fx, and body forces normally is the gravitational force, will have its value in the x component direction as this. Now, if this is the volume that we are considering, this is the control volume, in the x, y, z directions, and then the contributions of the velocity to the linear approximation is, as you can see here, and they are the values from all the faces of this cube. So for the x cube, we have shown, you can see from the blue dot, that the amount of fluid the amount of momentum that is entering and that is moving out of these faces. And their values are given here, and this is to the linear approximation. The same picture here, little enlarged, so that you can see it clearly, the directions, the amount of quantities, and we have taken the first term as approximation. So if I write down these values, then these terms can be written as this quantity. It can be simplified to this quantity, and remember, it's only the x component that we are considering at this moment.